The second talk of this part of the event is from Wolfram company. Maximilien Tirard is going to present it, and Wolfram company was kind enough to sponsor this event for the second time. The awards of the poster competition is coming from Wolfram, and they are also giving a tutorial. Maximilien, please go ahead.
Thank you very much. So I'd like to apologize first because I'm a bit ill. So if I might need to take a break to go and sneeze or blow my nose, but I'll do the best that I can. So yes, so I'm Maximilien. I am a technical consultant at Wolfram. So I use various Wolfram technologies to develop solutions for our clients, for our customers. And yeah, today I'll be giving a bit of a demo of what you can do in Wolfram, and maybe some of you have already used it. Maybe some of you might have heard of it. You may well have access to Wolfram, since indeed it's a paid product through your university, since many universities have agreements and site licenses. So it might be worthwhile seeing if you can get access to it through that, or we have free trials. But yeah, before that, yeah, I'll be giving a bit of a demo of what you can do with Wolfram. So right now I have a window open. This is a notebook. If any of you have used Python notebooks, this will be quite familiar. So this is sort of a blank canvas, and I can sort of start writing code. So I can do, computations. So I can ask, okay, what's 1 + 1 or 1 + 2, and I can get an answer, and that's already great. Wolfram is known for being very mathematically focused, so you can do a lot of different sort of computations and not be worried about how the idea being that you can do a lot of different computations very nicely. So there's no restrictions when it comes to floating point accuracies, or well, no, there are floating point accuracies issues, but yeah, you can do computations that go beyond what you get with integers, and you don't have to worry about defining your types. It's sort of all quite natural. Of course, there's a bunch of different functions built in. Now, here's a first sort of a pitfall that you might that's worth spending some time discussing briefly. So sine, of course, is the sine function. The square brackets here just means that we're calling this function. Square brackets are the syntax for that. But notice that sine of 10 isn't evaluating into anything else, right? Because as it turns out, this value of minus 0.54 is not exact, right? As it turns out, there are these things called transcendental numbers and algebraic numbers. And I believe, I forget if this is an algebraic or a transcendental, but at any rate, it's an irrational number unless you pick specific values, right? Like if we take like pi over 2, for example, or let's just do pi over 4. Actually, is it pi over 3? I believe. Is it 6? Yeah, there we go. Pi over 6. This is, in fact, an exact result. And so interestingly, you'll notice that we do actually get an exact representation here as a fraction, whereas here we do not. It sort of stays unevaluated, and so we need to use this end to say I want an approximation. But that's very nice because actually this is what you want, right? You want this. I don't know if you're familiar with the sort of the Casio calculators where you're like, oh, what's 13/21, and it's like, that's not very helpful. I want the actual, I want the approximate form. But no, actually, for the kinds of purposes here for mathematics, this is exactly what you want. And the reason that this is nice is because you're sort of dealing with symbolic expressions, right? This is, I guess, what we're going at here. What I mean by symbolic expressions is that if I say x, for example, and I just evaluate x, I get back x. And it seems benign, but is actually very important. If you do this in basically many other programming languages, you'll get an error saying, oh, well, what is x? X is not defined. And actually, this is exactly what you want, because we don't need to know what x is. X is a symbol. And for that matter, actually, I'll sort of start introducing this now. I'll start this thing called tree form. And so tree form sort of gives representation for objects in a sort of a tree kind of way. Now, as it turns out, it doesn't actually give symbols. I need to ask for head. Basically, my point is that x actually is represented as this under the hood, right? We have symbol x, right? So when I said x plus x plus x, effectively I've done this, and I'm getting back 3 times symbol x, right? And in fact, let me just do what I did here with this tree form because I think it's relevant. Yeah, so we effectively have this, right? So we're dealing with trees of expressions to represent objects. And I think that that's sort of is interesting about the Wolfram language, which is, the programming language that we've been seeing here before, because it's what underpins everything. Now, why is this neat? So we can do x plus x plus x, great, and then we get results. We can also do x, let's say, squared over x, and that understands what that is. And if I do something like x plus 2 over x, we can also simplify that, right? So we can manipulate expressions on their own. I would have expected that would have, it's probably the other way around, actually. If I do 1 plus 2 over x and I ask for this, I need to type that correctly. Right, there we go. So it knows to effectively take this this form, which is factored, or rather, which is unfactored, and it knows to transform it into a factored form, right? So it can sort of do these kinds of operations. And if we do sine of x plus sine of, I forget if this has sort of a simplification form or not, or I forget what rules exist for simplifying stuff. But if we do sine, for example, of this expression, right, there's plenty of identities that are sort of built into the language. We have this understanding, right, that this these expressions are sort of built in, and then that's what having these symbolic expressions allow, and that's all very nice. Okay, so that's sort of as the underpinnings of what the Wolfram language does. And you can do fun stuff too. So if you're a mathematician, basically, the answer is, it's very nice to do mathematics in the Wolfram language. And you can say, I want to have the solutions for x, and it brings you back those, right? So that's very nice that you can sort of do that. Or I could do, for example, I want to solve what values is sine equal to a half, and I want the values for x, and it sort of understands these representations for numbers, which is certainly very nice. And I think part of the value of this is that it's a mix between the algorithms that underlie doing this stuff, right? That's what a computer algebra system is, right? It sort of manipulates expressions, and there's in a sense there's nothing special about this, but what's neat is that it's been sort of threaded through the way that you write things themselves, right? So if you want to write a thing, you can you have these mathematically typeset things. If you want to talk about I don't actually use let's see. If I want to typeset, my window has opened up on my second monitor. There we go. So I can, there we go. Great. So yeah, I can construct mathematical expressions with all these different constructs, and this is the one I wanted to show actually. Is I can type in a matrix, for example, like that, right? And that is understood to be a thing, and I can then sort of multiply it by, is it in the right shape? Let me just have another. Right, so this is sort of matrix multiplication, but yeah, I don't have to write it out as lists of lists. I can just express it as I would want to as a mathematician, basically. So it's all very nice. So that's sort of covers the big ideas as to how you can do mathematics in the Wolfram language. Now there's also a whole sort of algorithmic side, which is pretty neat and interesting, and I'll sort of try to thread that in. I'd like to talk a bit about sort of functional programming now, right, which is sort of quite well suited to in the Wolfram language. So I talked about function application. So I said, sine of 10. This is how you say I want to apply the sine function to a value of 10. And in the same way that I can construct symbolic expressions, I can construct function calls on symbolic things. So I can say f of x, right? And as it turns out, I haven't defined what f is in the same way that I haven't defined what x is. And I can say, oh, I want f of g of x, for example. Or, and I've actually defined G in an earlier environment. So let me just clear all. That's a sort of G. There we go. So that's sort of that was stored in memory from previous. I'd actually assigned a value to G, which of course, you know, I can do things. I can do x equals 10, and then if I go back and evaluate sine of, you know, I can do then x squared will then of course give me back 100, but that's no longer a symbolic thing. So let me just clear x again quickly. So here we have sort of functions being applied. Now, what did I want to say about this? I wanted to talk about functional programming, and I wanted to talk about fold and nest and this sort of thing. So nest, let me just open up the documentation actually. So here's the documentation for the Wolfram language, and it's very nice because if we go back to, for example, the solve function here, I sort of gave some demos of how it worked, and just for the purpose of showing that it would, you know, that it knows how to do mathematics, but without necessarily explaining how or what it does or how to call it. And if I open up the documentation for solve, then it, you know, I can sort of go in and see all the stuff that it does and see some examples and go into that. So I think it's worthwhile saying that the documentation of the language is one of the highlights. We put a lot of work into it, and it's a really great resource. So I said nest, right? So nest is effectively a function where you give it three things. So you give it an f, an expression, and an n. So if I say I want to nest the function f on an expression x, and I want to do so, let's say, 3 times, then it applies f to x 3 times, right? And that's pretty neat. You know, it seems a bit arbitrary, but what's neat about this is that we can, it's an extremely general construct, right? And this is this sort of already pointing at the idea of sort of recursion effectively, or sort of repeated, right? This sort of algorithmically, this is pointing into a lot of interesting directions. Now, you know, there's almost no bounds as to the creativity that you can have here. So for example, if I decide that I want to apply it on 10, I can see that if I apply sine instead of my f, I can sort of start asking questions about, okay, well, what goes on as I sort of apply sine increasingly so? And, you know, now we're suddenly talking about the fixed point of a function, in this case, the sine function. And, you know, here, this is sort of a purely functional thing, and all of a sudden, this is sort of in the domain of analytic, you know, of mathematics and such. Now, as a sort of a fun aside, since it's there's some fun things here, the Wolfram language can deal with sort of in this notebook environment. I can interact with rich objects. So, for example, I can use images. So let's just take a screenshot. For example, I have, if I'm not mistaken, yeah, let me just take the schedule for the future algorithms talk. And let's say that I'm going to take a screenshot of this particular section here, right? I can then just paste that in, right? So this is an object in and of itself. And actually, what's interesting is if I ask for the tree form of that expression, I can actually see that it has sort of an expression, a symbolic expression of its own, right? Where we have an image header tag, and then we have actually a numeric array which represents the pixels of it. So this image is like 700 pixels wide and 300 pixels tall, and so that's, you know, the data is in there. So that's the sort of the idea. Great. So what's good about having sort of images built into a sort of a notebook environment is you can call functions like text recognize, and text recognize is a function that effectively does optical character recognition on an image. As it turns out, you know, this is just text in and of itself, so I can just copy and paste this, and indeed it's just you know, it's just strings of characters. So that's sort of a nice little usage of it. Now, why was I bringing this up here is if we take a function like edge detect, right? So let me actually just show edge or detect edges. Normally I have, yes, there we go. So this is the edge detect function. You give it an image and you get back a detected edge. So this is a classic sort of image processing technique that's sort of built in, which is nice in and of itself that you can just do this without having to import a library or figure out what parameters to call it with, or if it's, in the right sort of compression or encoding technique. But what's even nicer is that we can just say, I want to do an edge detection on my image 10 times. And that'll just apply the edge detection 10 times to that image, which I think is pretty neat, that you can sort of do sort of higher level programming very easily with these things. Effectively, the sort of the ethos is we have these sort of super blocks or super functions that you can then, like Lego bricks, glue together in a sort of a cohesive ecosystem that you can do stuff with. And if I'm not mistaken, there's also the blur function. Let me just remember what syntax it is that we're expected to take here. I can actually do current image, and I'm going to apply blur to the current image, let's say 10 times. And that's nest that I want here, and blur. And so current image takes uses my webcam to get an image, and then I'm applying blur to it 10 times, right? So sort of fun little things that you can do here. Now, actually, if I'm not mistaken, we talked about fixed points earlier for the example of applying sign to a function multiple times. But there's actually a fixed point function here, and I can call the fixed point of sign, say on 10, and if I'm not mistaken, it will just run and figure out where that ends up. Now, I believe that because it's numeric, actually, that might not work. But maybe what would be a nicer example would be, yes. So let me just define a function such as, let's say just some degree 3 polynomial. So let's do, for example, say this. So now I've actually given a value to f, right? This function f. As it turns out, I can also just use some of the nice plotting functionality that exists within the language. So I can say that I want to plot x between, say, -3 and 3, for example, right? So this is a nice little quadratic. And indeed, again, I'm in a notebook environment. I have this sort of built in. I can interact with it. I can play around with it. It's very nice. Now, I'd like to show, basically, I'm sure most of you may well have heard of or are familiar with Newton's method, and indeed used to find roots of differentiable functions. And I can actually use the fixed point function for that. So if I apply this sort of iteration, and actually, before that, let me just show off that if I ask for f of x, right, that's that, but I can actually ask for f prime of x. So that's the derivative of this function at a particular point. Can I actually, yes, so it's computed the derivative by applying the linearity of differentiation. So, this 3 has now gone down here, the exponential, or the third power is now a second power, and, computed the derivative. So I can actually refer to this derivative here, and actually let me just use this slightly different syntax to make this perhaps a bit clearer, right? So I am now here. I've effectively encoded one step of Newton's root finding method, and if I apply it, indeed, I get back this sort of result here, which claims that an input x of 2.09, which indeed we can sort of verify, is thereabouts the fixed point of iterating on this, right? So, yeah, Newton's method, very important function or concept, and you can just effectively express it arbitrarily as by using this fixed point function. So, very powerful stuff, very fun, that you can sort of use these functional constructs to get very far. And that's without even mentioning functions like fold, which allow you to sort of break things in. Actually, let me show you briefly an example of using fold. So let me talk about continued fractions. So continued fractions are a way of expressing irrational numbers, or of approximating irrational numbers with continued fractions. So a continued fraction is going to be something of the form where we have a, it's going to be something basically like this, right? Where we have something that sort of expands like this. And I hope that this is not too small, so let me just change my size a bit. So that's the idea of a continued fraction. And if we do something like 1 plus 1 over 1, and then 1 over 15, and then 1 over 7, I believe that this should start approximating, I forget which function it is that we're supposed to, is it 3? But yeah, effectively, if we take the continued fraction for, I think it's 1, 15, 7, 3 to start with, and 292, and then we apply the function. So here this syntax notation was effectively a lambda function, which you may be familiar in other programming languages. We're effectively introducing a function where here this is the parameter, and here this is the output, and here there's a single input to this function, and we can actually use multiple inputs by using these sort of slots by using this, right? So if I use this as the second slot, and that's the first slot, and I'm going to wrap this in a function to say that, this is an abstract, an anonymous function that I'm introducing, right? So effectively, we're saying I'm going to start with, sort of wrapping things in this way. So let me actually do fold list. That way we can sort of see this thing converging. So we're actually constructing it bit by bit. And actually, let me just copy this over, but let me make it abstract. So I'm going to start with, let's say, an X, and then A, and then B, and then C, and then D. And the neat bit about this is, because I can express things symbolically, I can sort of see what it looks like through these symbols, right? So fold list returns the iterated results of applying this function to this, whilst also merging in this other list. So we start with just X, right? We've not done anything, and that's the first result from our fold list function. The second one is after applying this first argument, this function here, once. And indeed, what it's doing is it's taking our previous result X, right, which takes in the slot of 1, and we're putting it here. And then we're taking whatever second thing, which is going to be successively A, then B, then C, and then we're putting it in this first position, right? So that's how we get A plus 1 over X. And then we keep sort of iterating on that. So this A plus 1 over X then takes on that place here whilst we add in the B. And then this entire expression B gets folded into here whilst we add the C. And then this entire expression here gets on, and so on and so forth. And when we apply that for the sort of the continued fraction for pi, which is sort of corresponding to this list here, where we actually start off with 292, which is sort of the approximation that we have here. That's how we sort of progressively get to pi. So that's a fun little connection between folds, or a way of expressing continued fractions with folds. So yeah, that's quite nice. Now, one of the things that I quite like about the Wolfram language is the fact that it, here we're dealing with mathematics. We were dealing with sort of plots and these sort of rich objects. And we are also dealing with these sort of images. But you can also make stuff that's actually interactive. And that I think is quite neat. So, for example, let's just do something like A plus B to the power of 3, right? That's just an expression like any other. But we can actually ask to have that expanded. And that sort of expands it out in the way that you would be able to do. And for 3, I'd expect most people would have this committed to memory. Maybe not for 3, but you could probably work it out if I gave you a minute. And then maybe for 4, same so, or it can get kind of annoying, but you sort of work it out. If I then wrap this sort of entire expression in what is called a manipulate, I can then effectively construct something that's interactive, where I can sort of start with n equals 1 and then say, actually, I want n equals 2. Except I need to specify that the increment is integers only. So there we go. So 1, 2, 3, 4, 5, and so I can sort of create these interactive things and see how it all moves together. Now I heard there was a GeoGebra mentioned earlier, and indeed, you can do something very similar here. So if I want to plot a function like sine of ax, and let's see, no, x is still not defined, so we're fine. I want to plot that with x going from 0 to 10, for example. So that looks fine on its own, but I'm going to now wrap this in a manipulate. And I'm going to say that I want to manipulate the variable a, and I'm going to now make effectively the frequency of this b variable. So I can see that I can vary how that the plot of that function by manipulating the variable for a. And that's quite, it's very neat that you can interact all these things together. And in fact, if we take, again, this expression here, we can do, we can combine all these things I mentioned earlier, sort of building blocks or Lego blocks, and that's very much the idea. So if I do an edge detection, but I nest it a variable number of times, then I can see that I can control or see how much sort of combine these things in very nice ways. So yes, when it comes to doing computations, whether it be symbolic or numeric, it's a great place to be. But in a way that connects to computation, I would now like to talk about quantities and about things that start touching on the real life. So what I mean by that is, if I talk about something like the number 10, that's just the number 10. But 10 what, right? Here we're talking about a sort of a unitless quantity. And unsurprisingly, there's this thing that is units, right? So 10 what? 10 meters, 10 kilograms, 10, and so on. And that's exactly what the quantity function allows you to do. So I can say, oh, I actually have 10 meters. And that represents, conveniently, it's sort of represented in this slightly brown color, and that works out quite nicely. So I can talk about 10 meters, I can talk about 10 minutes, and that's a sort of a unit of time. And I can do unit convert, which is a nice little function. If I want to, say, convert minutes to seconds, I can say that, oh, well, 10 minutes is 60 seconds. Very nice. Or perhaps less intuitively, I can say that 10 meters is actually, and I need to then do the approximate form of that, 32.8084 feet, for example. Okay, so this is sort of kind of standard, and that's not necessarily surprising. Tools like Spotlight can also do that computation for you, or if you ask Google, it'll do that also quite well. So this is perhaps not quite so surprising. But where this starts being interesting is when you start combining it with other things. So for example, if I know that I walked to do my groceries, and it was, let's say, 1.3 kilometers that I did, but that it actually took me 45 minutes to do that walk, then I can see that on average, that was the speed at which I went. And what I think is really neat here is if I look at the tree form for this, you'll notice that indeed we have a quantity, but actually what's on the, well, maybe tree form is not the way, let me just show input form, right? This is actually being represented as kilometers over minutes, right? So we have this sort of kilometers over minutes representations, right? And so these are strings, right? We're dividing a string by another string, and I think that's delightful. And we can actually talk about stuff like meters squared. Let me just do this nicer notations. Meters squared per second, right? That's totally valid, and I can talk about, in fact, 9.81 meters per second, right? Taking the string meters and squaring it and dividing it by seconds, I think that's brilliant. And so this is very a convenient tool when you're doing dimensional analysis, and there's plenty of very nice units that are supported. So I can talk about moles, for example, and that's of course in chemistry the relevant thing. And so for all of your different needs, that works quite very well. And in fact, it also works very nicely with functions like around, which allow you to express effectively uncertainty. Right? So I can talk about the sort of plus minus 1 here, or let's just say 2. And that corresponds to sort of the uncertainty bounds between a measurement, say. So let's say I measured a bridge that's 10 meters tall, but it's my accuracy was very bad, or maybe my accuracy was better, so this would be 2 centimeters. Well, I can actually say exactly that this is, I measured my bridge to be 10 meters, and yeah, I'm getting a helpful error message that these things are not comparable. But I can say that my uncertainty was 20 centimeters, for example, and that works quite nicely, right? And then I can obviously do computations such as adding, let's say, 2 feet, for example, and it knows to do those computations, and it does all the things nicely. So that's nice. I started off saying that I wanted to talk about the real world, and the reason is that this then connects to the sort of the entity system within the Wolfram language. And so what that is this. So entity, right? Great. What is entity? So I can talk about different kinds of entities. So for example, I can talk about planets, and I can talk about the Earth, and that is a thing, right? And you'll see that it sort of has a nice little box, and that's cute. And what's great about this is I can ask it about things like its mass, for example, and I get the mass of the Earth. Or I can talk about its mean radius. Was that a thing? No, that's not the right one. Radius, there we go. And I get the radius of the Earth. And where this starts being nice is that I can do stuff like I can take one standard gravitational constant that I will then multiply by the mass of the Earth, and that I will then divide, let me just take that entire expression and divide it by the radius of the Earth squared, and that gives me back, I want to then unit convert that, I believe. Or am I missing? I need to, so let me unit convert that to what I expressed here, which was meters per second squared, although I've got a kilogram, so, oh, it's kilogram G. That should hopefully cancel out. No, it's not comparable. I would have thought it was. Well, I've messed my demo up and my physics is a bit rusty, but in theory, if I'd had the correct expression, which I'm sure one of you will have in mind, ready to go. But yeah, this units such as these ones are built in, so you can do very nice computations like that. And so we have things for example, the Earth, right? And we can ask about a bunch of different astronomical properties about the Earth that are sort of built in, including sort of astronomical properties about its semi-major axis. But we have plenty of other entities. So I showed off this Earth was a planet, but we have things like, well, let's just do France, since that's where I'm from. Entities such as countries, such as France. You can ask about France's population, for example, and you can get a result. And mind you, so it's maybe not surprising that when we were asking about the mass of the Earth, that was sort of considered to be a constant. But as it turns out, when you ask about the population of a country, that actually is making a request to an API. Now, as it turns out, this result was cached and stored. But if we go back 5 years ago, or if we go 5 years into the future, this result will actually be different. And actually, one thing which I find fun in is if we go to examples for country data, for example. Here, yeah, so here's the GDP of France in 1970. The documentation has conveniently found examples which are sort of fixed and don't. Oh, there we go. Actually, yeah. So if we ask for the population of France, this is here listing it as 6.3 or 63 million people, but now it's 66 million people. So if I rerun this result, since indeed the documentation was sort of pre-stored, now we're getting a sort of a different result. Now, interestingly, that's sort of a different number, but that's fine. Now, why is this sort of neat is because you don't have to bother with finding APIs or with data sets for standard sets of data. So if you're doing anything that's involving statistics, or you want to do some analysis or find some correlation for things, you can very easily have access to a whole load of different stuff. And again, here's, because we have stuff like population, we also have access to stuff like land area. And that is a result in another quantity again. So I can ask about the population over its land area. And I see that there's an average population density of 120 people per square kilometer. And I can do stuff like, let me just entity country, let's say Germany. All right, so that's Germany. I can then do the same computation effectively for Germany and get a much higher population density. Indeed, so the population of Germany is very large, and its land area is comparatively smaller. So you can do very, very fun computations very easily in that kind of way. And as it turns out, you can go even further than this and use functions like geo-region value plot. And you can ask for stuff like the European countries where we're plotting their population density. Now, it turns out population density is something that's actually built in. And the scaling is wrong for some reason. Let me just ask about the population. That'll be hopefully nicer. There we go. And yeah, I can just immediately ask for a plot of European countries where we're showing their population on a color plot. And yeah, I don't know. It's very nice to be able to sort of immediately both be able to do computations, get units done correctly, do visualizations. And here, we didn't, I don't have an example ready, but there's things like correlation, for example, and that's between vectors in this case, but you can also compute the covariance, for example. So if you have a large data set, you can go through a list of countries, take their population, take whatever other quantity. In fact, actually, I have a demo ready here. So let's just plot. Bam, bam. So what this is we're defining all countries. So that's all the countries that is in the database here. We're defining a sort of a list of properties, including GDP, population, life expectancy, all these sort of stuff. And here we're creating this sort of manipulate that I showed earlier. This is what expression is being manipulated. But the interesting thing here is that we're choosing between two different properties that we can manipulate, and we're choosing it from this list of properties. So what that looks like is we're making a log plot where we're plotting, in this case, the GDP on the x-axis and the population on the y-axis. And I can actually say that I want to compare it to something else. So maybe I want to compare the GDP to the life expectancy, for example. We can see that maybe there kind of is maybe a correlation, maybe not super clear. But maybe if we compare the population to the population density, well, actually, surprisingly, it's kind of constant, right? So there's not maybe a correlation between that. Or maybe if we compare the GDP and I'm not sure. No, GDP and area for some reason is correlated. Maybe that's not surprised. There might be a sort of a constant amount of GDP that could be generated per unit of area of a country or something like that. So, and again, this is just so happens that we were using countries here as a sort of an object of study, and that these are the properties that we were sort of taking a look at, but there's no reason that we could want to look at planets instead, or any other number of entities that are sort of built in. And there's a whole host of entity types. So there's plenty and astronomical. So we've got a database of stars, of planets, of moons. We've got plenty of things in terms of like languages. So you can ask, okay, well, what are the different languages that are here? What are the countries that speak these languages? So, if you're doing anthropology or sociology, there's plenty of great stuff there. There's books, artworks, movies. You can ask about famous people. So I think that we can even do like David Bowie, for example. And I can ask about David Bowie's spouses. And I can see that David Bowie has had 2 spouses in total, for example, right? This is sort of the kind of stuff that you can do. Now, I think that I've sort of babbled on quite a bit already, and I wanted to show a bit of an example of something that I worked on to help some people at the University of Sorbonne with a project that they were working on. So this was effectively a project where they had an image of a slime mold that they had taken. So what that looked like was effectively they had something that looked like this. So they had a slime mold. I don't know if that was the image that I have. Yes. And if you look into its structure, it sort of is in a petri dish. So that's the circular outline that we see here. It didn't quite grow up into this top right corner, but it sort of spread out to the rest of the edges. And it sort of has a sort of a big body in the center. That's maybe it's sort of like its core. And then it has a bunch of dendrites that sort of stray out and sort of reach out to the edge of the sort of the media, which contains, I think it's nutrients, some kind of food that it was using to sort of feed itself. And what these researchers were interested in was understanding the mechanics of how these nutrients sort of propagate as they get sort of ingested at the edge and then brought back into the center. And so they had these images of this petri dish that they then wanted to be able to do computation on. And so this is what we were doing here. So there were sort of multiple steps. I was talking about Lego bricks, and indeed here, this was a good example of sort of pulling all of these things together. So part of the sort of the starting bit was this image. So there were some image recognition tasks going on here, since we needed to sort of do edge detection to figure out what the edges of what is a part of the slime mold, what is a part of the ambient media. And then we needed to do some further processing to extract a sort of topological representation of it. And that's where you can see these little points and edges between them. Effectively, we're constructing a graph out of this image. And so that's what these little red crosses are. And we have like one big node here, and then it sort of pulls out to, so that's what these are. And then we're sort of modeling the slime mold as a graph. And once we have this graph, we're starting to do some interesting computations in this. So here it is as a graph, unfortunately rather faint. I think I have better examples further down. So there we go. So here's the sort of the graph representation within the Wolfram language of this object with blue little nodes and gray lines between them. And so why did we want this as a graph? Is because we can then effectively solve a set of equations on this graph to model the flow of nutrients, where effectively every node now has a nutrient density, effectively, and then all of the edges they correspond to sort of derivatives or sort of taking nutrients from one node and then depositing it on another node. And there's these diffusion equations that dictate sort of in the same way that when you have like tanks that are communicating, they'll sort of equilibrate towards having a sort of an equal level at a speed that's proportional to the differential of levels between the two. And so we sort of define a Kirchhoff matrix off of this graph. And that's sort of the way of expressing this sort of relationship that we want we want to conserve quantity. So, as our system, as we model the nutrients moving around, we want to have conservation of nutrients. We weren't interested in modeling the fact that this nutrient might be consumed, for example. We just wanted to model how it would flow throughout. And then effectively, there's just some interesting mathematics related to Kirchhoff matrices and graphs and all these stuff. And here's actually an example of nest list that we were using here to try and solve it using discrete steps. And as it turns out, this is sort of showing how, as time goes on, initially we have a sort of a non-uniform distribution where we were modeling. This is a histogram of the nutrient levels where at the start, some of them were low density and some were high density. And as sort of we move on through our modeling, we see that as we would expect, it sort of converges towards an average as these nutrient levels come to equilibrium. And here's sort of showing that plot over time, where we have one that's a very low level to start with, that sort of goes up, and then one that's a relatively higher level, and that goes down. But as it turns out, we actually had some instability issues, and so we actually turned towards a model where we were modeling time continuously rather than in discrete steps, right? So here we were using a nest list, right? So each step being discrete, where we're using our model. And then we moved away towards using a continuous solution, and that ended up being much more stable and working quite nicely. So indeed here we, again, slicing our histogram at different times. So we actually ended up using the ndsolve value function here, which is what we're doing here. So we've got our set of equations and our set of starting conditions and the variable over which we're iterating, the details of which, if you're interested, you can go and look at the documentation for this function or in your own time. And then we can sort of, once we've solved this, we actually overlaid the results back on top of the graph itself to sort of represent those densities sort of moving about as we go. I guess this, I'm not sure if this result works here. Yeah, but yeah, so we can sort of use the various plotting functions to get that back overlaid to show how this sort of system evolves over time. And I think that this is a sort of a nice little example of putting everything back together, starting from raw data, doing processing that's in sort of multi-domain with images and then graphs and then equations and sort of putting it all together in a way that's sort of quite satisfying again here. I heard there was a talk about backgammon, so this was, I don't know if I want to take a bit of time to mention sort of another exploration that I had recently as a side project, which involved Scrabble. So I maybe won't go into too much detail right now, but I have a colleague who was interested in Scrabble games, and so he made perfectscrabblegames.com. So if you're interested in Scrabble, I would, this is a bit of a plug for my colleague here who had fun. And so the game is trying to find perfect Scrabble games where every player uses all of their tiles every single time. And I'll encourage you to look into this a bit more. But I thought it was a fun combinatorial problem, and I actually ended up using a bit of Wolfram code, and effectively it's an integer linear programming problem. So I thought that was a fun little side project that I did involving that. So I don't know if it's not directly related, but something I thought was interesting. And I would encourage you, if you're interested in Scrabble, to go and take a look at that. I think that I might, yeah, if there are any questions right now, anything that you would like me to go more into detail about, or anything that you thought was interesting, please let me know.
Okay, let's thanks Maximilien Tirard for the presentation. If you have questions from him, we have 7 minutes for the questions. Any question, or should I start myself? So some of these data, like the country population and other numbers and stuff, are they locally stored with the software on the device, or it is going to read from online references?
It uses online references for things, but it does cache them. So if it's the first time that you're requesting it, it'll go and fetch it. Otherwise, it'll have them locally.
I see. Any question from the participants? Well, until people are thinking, I can ask another question. So most of the math software have this function called simplify, but so far I don't think there is a globally agreed definition of simplify, like which expression is more simpler than the other one. Sometimes you may be interested to get rid of the fractions. Sometimes you want to have less number of arithmetics. For example, the one that you showed, 1 + 2 over x compared to 2 + x over x, both of them use 2 arithmetic operations, so not much difference, but maybe someone wants to make the common denominator. So what definition is Mathematica or Wolfram is using?
I wonder, actually there are sort of different things that you can tell it. So I think you can tell it to do trigonometric simplifications or not. So for example, here, let me just bump that up a bit. You can tell it that you do want it to take this expression and understand or not. So if you tell it don't simplify, then it won't use trigonometric identities. So that's one of the things that you can pilot, but that's sort of turning on or off some of the rules for expressions. There's transformation functions. I don't know if there's anything that you can do in there, but yeah, you're right to effectively say that I don't think there is or should be a standard answer as to what is considered canonical as a representation of arithmetic. Generally, the idea is that it does a sort of a sensible job with sensible defaults, and I believe that if you do want to plug into the details, which I've not had the occasion to do myself, but you can go and control it. But that's a good question.
Okay. Maybe I ask one more question, and then if there is no more question, we can stop this. Are there some packages in Wolfram for doing machine learning, reinforcement learning, and these trendy AI stuff?
Yes. So there's effectively two main functions in here. So there's classify, and effectively the way that you use classify is you give a list of examples as a form of rules. So for example, let's say, yeah, and then let's say 10, for example, is going to go to B. So here we have sort of a classifier on one variable where we have this 1 goes to A, 2 goes to A, and then 10 goes to B, for example. And that sort of creates a classifier function, and then I can sort of call that on the values that I want. So if I can say, oh, well, what's 4 going to go to, and then what's maybe 20 going to go to, something like that. And indeed here it sort of chose logistic regression for its method. But you can specify that you want to use something else. So for example, I can say that I want the method to go to a decision tree, for example, and that'll use that as a sort of a method, and that'll work in the sort of same kind of way. And there's different classifier measurements. Well, I think what's neat about this is that the syntax that you use in order to call this function, you're not saying, oh, train a neural network or train a decision tree. You're just saying, I want a classifier, and as it so happens, I want to use this particular structure or this particular method. And so it's very easy to sort of switch between different methods and to compare your models against one another when you're doing your decision. And as it turns out, if you don't specify anything, it actually does cross-validation of models using your data. Now, obviously, this is sort of a dummy data set, so there's not much to do here, but it sort of does that with its own interesting heuristics to sort of pick something that's sensible. And there's plenty of functions for extracting sort of measurements about your classifier. So if we look at something like the MNIST database, so handwritten digits from 0 to 10, you can do stuff like the confusion matrix, showing the predicted class versus the actual class. So we can see that most of the things fall along the diagonal, for example, and you can see, oh, well, there's a lot of confusion between 9s and 4s, for example, which makes sense given that they sort of kind of look the same. And all you need to do is call the syntax for that is also quite nice. And then all this stuff about classifier has its analogies with predictors, right? So that's going to be whether your domain is continuous or discrete, right? That's sort of the analogy that exists here. And if you want to do neural network stuff, there's also a whole framework for that in a similar kind of way. And there's also a database of neural networks in the same way that I can just say, oh, well, what's the population of France? I can ask about neural network, and then I forget. But yeah, there's a database of them that you can effectively download. And then if you want to do some fine tuning, you can just say, I want that network, but I only want to chop off the last 3 layers and I want to build my own on top of it. That's net chain, I believe. So you can say, oh, I want this kind of a layer, and then I want to, there's a very nice framework for it. And it's all accelerated with hardware too, locally.
Okay, thank you, Maximilien Tirard. Thanks the speaker again.